Hi, my name is Armando Hererra Uribe, and I will be talking to you today about a PID controller. Basically, we need to understand three things that we'll be seeing throughout this video, which is the introduction, what is a PID controller, how does it work, and why is it useful, a working mechanism involving the PI and the D parts of the PID controller, and a very brief and specific example of how a PID controller could be implemented in a controlling industrial system. So first of all, a brief introduction about PID controllers. Basically, a PID controller is a very useful system or tool to be implemented in different systems in order to control process variables. These process variables can be different regarding different systems, and they are temperature, flow, pressure, or speed in most of cases. And the PID, which stands for proportional integral derivative controllers, are able to create a control loop feedback mechanism that will provide information and will be making able the PID controller to change its process variables and move them towards a set point. This set point is usually given by the user of the system, and it's like an ideal state or where the system should be working to achieve a desired result. And this is why the PID controller is thought of the most accurate and stable controller. It is important to mention that this type of controller is expected or recommended for systems where the load changes often and the controller is expected to compensate automatically these changes, or when the set point can be changing throughout a given period of time. The importance of a PID controller, as I already mentioned, is that the main objective is to create a feedback loop and force it to match the set point. This allows it to be very versatile and achieve different states throughout the system and really compensate whenever a mistake or an error occurs. One quick example about this is how a thermostat will be able to change the heating unit and turn it on or off depending on the feedback and the temperature received. So that is an example of how the loop will be working throughout the system. Talking about the working principle of a PID controller is that, as the name implies, the PID controller combines the proportional control with an additional integral and derivative adjustments that will help to automatically compensate any errors or changes in the system. Basically, the proportional, integral, and derivative terms of the PID controller will have to be tuned depending on the differences between the values or the correction factor. And the correction factor, in fact, will be calculated and applied to the input. For instance, following the same example of the temperature, if the temperature of an oven is below the set point, then the heat will be increased. Talking about the three parts of the PID controller, we could understand that the proportional tuning will be working to correct a target proportional to the difference. It is important to mention that this target value will never be achieved fully because as the difference approaches zero, so does the applied correction. So that's why integrating or adding the integral tuning and the derivative tuning makes it more accurate to be implemented in this type of systems. The integral tuning works by attempting to accumulate the error that is resulting from the proportional tuning part and increases the correction factor. And finally, the derivative tuning works by attempting to minimize the overshoot that will be created in the integral tuning, and the correction factor will be applied in the target to be approached. Following the same example, once again, of the temperature and the oven, we can understand that for integral tuning, if the oven, for example, remains below the temperature that it's given, the integral tuning will try to increase the amount of heat that is being delivered. Rather than stop the heating when the target is reached, the integral tuning will try to attempt to accumulate the error to zero, resulting in an overshoot. So the integral tuning will never stop the flow of heat, rather try to smooth it, but this will try to smooth it, and this will cause an overshoot that will be corrected by the derivative tuning. We have three types of different PID controllers. Basically, they depend on the system we are working with and what process variable we need to control or smooth. For instance, we have the on-off controller. This is the simplest form of a PID controller, which depending on the feedback of the system, the PID controller will actually turn on and off the different machinery that will be providing the inflow to our system. There will be no middle stage, and we'll switch the output only when the temperature crosses a set point, following the same example once again of the temperature, but it could be applied to different process variables, such as speed, flow, mass flow, molar flow, etc. The proportional controller, which are designed to eliminate the cycling associated with an on and off control, and the standard PID controller. This combines the proportional control with an integral and derivative control, as we already mentioned, and this allows the unit to automatically compensate any changes in the systems. And it's important to mention that these changes, or the integral, proportional, or derivative terms, accordingly, are expressed in time-based units. A very brief example of application of a PID controller could be this diagram that I showed in the previous slide. Basically, it is an example of a PID controlling the temperature flow or the temperature in a furnace in a whole system. Basically applying a PID controller to be an applicator of control in our system, basically depending on the feedback that will be sent from the furnace, more specifically the temperature, the PID controller will compare it to the set point that it's given by the user and make any adjustment to the gas flow to the furnace. This allowing to create changes on the combustion reaction and hence changing the temperature and moving it towards our set point. And basically, the controller is usually just one part of the temperature control system, but the whole system should be analyzed and considered in selecting the proper controller. That's our references, and that will be our brief walkthrough about PID controllers. Thank you very much.